Hello everyone, from this particular video, we will understand the difference between stiffness and flexibility matrix method. And for that, we will use one particular cantilever beam problem. Now, matrix method is a modern approach to structural analysis that uses matrix algebra to solve complex structural problems. It serves as the foundation of finite element analysis. Why matrix method? Because it is systematic approach, it is compatible for computer programming, and versatile for different structural elements. Now for matrix method, two primary approaches are there: flexibility method and stiffness method. Flexibility method treats redundant forces as unknowns, while stiffness method treats nodal displacement as unknowns. Stiffness method is industry standard as it is easier to automate for different support conditions. Now, for a spring, if force P is applied and displacement is delta, then P equals to K into delta, where K is the constant of proportionality. So P equals to K into delta. Now, if P is constant, then delta will be inversely proportional to K. That means, for a spring, if K is more, the spring will be more stiff, and if K is more, then displacement will be less. So if we apply same amount of force, but if the spring is less stiff, at that time displacement will be more. If it is more stiff, then displacement will be less. So this is the basic concept of stiffness. Now what is flexibility? Flexibility is 1 by K. That means if it is more stiff, it will be less flexible. If it is less stiff, it will be more flexible. And when it will be more flexible, for same load, the displacement will be more. So this is the basic concept of flexibility and stiffness. Now for matrix also we use the same concept. For matrix, P equals to K into delta. Here, P is the nodal force vector, delta is the nodal displacement, and K is the stiffness matrix. For flexibility, the matrix will be opposite. For flexibility, the matrix will be delta equals to F into P, where F is the flexibility matrix. This will be flexibility matrix. Now actually, if we basically understand that actually K matrix will be inverse of flexibility matrix. Stiffness matrix will be inverse of flexibility matrix. That is very simple thing. From mathematical consideration, we can easily understand that stiffness matrix will be inverse of flexibility matrix. But it is not all. Actually, there is one basic thing for these two concepts, basic difference between these two concepts. The basic difference is that when we are calculating, when we are determining the flexibility matrix, at that time we apply force at different node. And by applying force at different node, we measure the displacement. But when we go for stiffness matrix, in this approach actually we apply the displacement at different node and then we measure the nodal reaction force. So actually both this method is technically different and the visualization of both this method is actually totally different. Because in this method we provide force and we measure displacement. In this method we apply displacement and measure the reaction force. So how we can calculate, how we can determine the stiffness and flexibility matrix, that we can understand from a particular simple problem. Now, this is one flexibility matrix. Now what is delta 1? Delta 1 will be equals to F11 P1 plus F12 P2 up to F1n Pn. Suppose these are different nodes. This is node 1, this is node 2, 3 and up to node n. So if we apply some force P1 at node 1, there will be displacement for different node. Now suppose there is some displacement for node 1 and that displacement will be F11 P1. Now after P1, if we apply force P2 at node 2, then there will be displacement for different node. But there will be also some displacement for node 1. And that displacement will be F1 to P2. Similarly, for different force, when we will apply one by one, then there will be some displacement for node 1 due to different force. And due to Pn also, there will be some displacement of node 1, and that will be F1 and Pn. So actually delta 1 is the displacement of node 1. But for different force, these are the different part for different force. Like when we are applying P1, at that time the displacement of node 1 will be F11 P1. This part F1 to P2, this will be also the displacement of node 1. But this is due to the force P2 at node 2. Similarly, this F1 and Pn is actually the displacement of node 1, but due to force Pn at node n. So delta 1 has different part, and these are the different part for different load. So if I again repeat, what is F1 to P2? F1 to P2 is actually the displacement of node 1 due to force P2 at node 2. So F1 to P2 is the displacement of node 1 due to force P2 at node 2. Similarly, F1 and Pn will be displacement of node 1 due to force Pn at node n. So this is the concept. So now, what will be F12? F12. If P2 is 1, then this part will become F12. So when P2 will be 1? When the force will be unit force? So F12 is actually the displacement of node 1 due to unit force at node 2. So F12 is the displacement of node 1 due to unit force at node 2. Similarly, what will be F21? F21 will be displacement of node 2 due to unit force at node 1. Now, from Maxwell's reciprocal theorem, we know that displacement of node 1 due to unit force at node 2 will be equals to displacement of node 2 due to unit force at node 1. So basically, F12 will be same with F21. And in general, we can say that Fij will be equals to Fji. And this will be based on Maxwell's reciprocal theorem. That we know that from Maxwell's reciprocal theorem, we know that if we apply unit force at node 1, there will be some displacement at node 2. This is the displacement. If we apply same unit force at node 2, the displacement at node 1, these two will be same. These two displacement will be same. So if force is applied at node 1, the displacement at node 2 will be equals to force applied at node 2, the displacement at node 1. These two things will be same. So based on Maxwell's reciprocal theorem, we can say F12 will be equals to F21. Similarly, F1n will be equals to Fn1. And all this term will be same. So basically this matrix is one symmetric matrix. And if we hold one particular mirror along the principal diagonal, then actually this term on this side of the mirror and the term on this side of the mirror, both this term will be same. These terms are actually same. These terms are actually same. So if we place one mirror along the principal diagonal, then the element at both sides of the mirror will be actually same. So this is one basic property of flexibility matrix. Now, this is one stiffness matrix. Now, similar to previous problem, what will be P1? P1 will be equals to K11 delta 1 plus K12 delta 2 up to K1n delta n. So actually for the previous case, we have provided different force at different node. Now if we provide different displacement at different node, if we provide displacement delta 1 at node 1, if we provide displacement delta 2 at node 2, then what is the reaction generated at node 1? That is actually P1. Due to displacement of different node, there will be some reaction force that will be generated at different node. Now, the reaction force that is generated at node 1 is actually P1. So, what is K11 delta 1? K11 delta 1 is actually one part of P1. Now, K11 delta 1 is actually the reaction force generated at node 1 due to displacement delta 1 provided at node 1. Similarly, what will be K12 delta 2? K12 delta 2 is force generated at node 1 due to displacement delta 2 at node 2. Displacement delta 2 at node 2. So, what will be K12? K12 is force at node 1 due to unit displacement at node 2. Due to unit displacement at node 2. Similarly, what will be K21? K21 will be force generated at node 2 due to unit displacement at node 1. And like the same previous concept that from Maxwell's reciprocal theorem, we can say Kij will be equals to Kji. Because force generated at node I due to unit displacement at node j will be equals to force generated at node j due to unit displacement at node I. So again, like the previous previous case of flexibility matrix, these elements will be same. K12 will be equals to K21, K1n will be equals to Kn1, and all the term, if we hold one mirror in this particular position, all the term in this side of the mirror will actually be same with this particular term. This term will be same. This term will be same, and this matrix is actually symmetric matrix. So if you do the transpose of this particular matrix, then it will be same. And also the matrix is square matrix, because along both row and column, if we think about it, the term will be the total number of term will be the total number of node. Or if we say it clearly, then total number of term will be actually total number of degree of freedom. Because for a particular node, there may be 2 degree of freedom. So if there are multiple degree of freedom, then actually both will actually cause different type of displacement in different direction. And that will be easier for you to understand if we go for a particular problem. Now this is one cantilever beam problem. Now this is node 1 and this is node 2. We know that for node 2 there may be some force, there may be some movement at node 2, and there will be some displacement and there will be some slope that will also generate at node 2. Now before going in that calculation, let us first revise one basic concept of coordinate system and degree of freedom. Suppose this is x coordinate system, this is y coordinate system, and this is z coordinate system. The displacement along x will be u, the displacement along y will be v, and the displacement along z will be w. Similarly, the force along x will be fx, the force along y will be fy, and the force along z will be fz. Now, what will be the direction of movement? The direction of movement will be based on right hand thumb rule. Like if we know that if we put our right hand, and if this is our thumb, this thumb is along the particular axis, then rest of our finger, that finger will actually show us the direction of the moment. So if this is the direction of force Fx, then this will be the direction of moment Mx. So this is the direction of Fx. If we put our right hand, then this will be the direction of Mx. This will be the direction of My, and this will be the direction of Mz. So always we'll determine the direction of moment based on right hand thumb rule. Now, for cantilever beam problem, normally there will be some force and moment in this particular node. So if we consider the positive force, then positive force will be along the upward direction, because we are considering the upward direction is actually the positive y direction. So if the force is along the upward direction Fy, then it will be positive. If it is downward, then it will be negative. Similarly, for moment, actually, if we consider the moment here at node 2, that moment will be Mz. Because normally for our beam, normally the moment looks like this. If we think about right hand thumb rule, then that axis is actually the axis, this axis. This is actually Z axis. And if we think that this is the positive z direction, then based on right hand thumb rule, the anti-clockwise direction of movement will be positive. So if we apply some anti-clockwise movement here, that moment mz will be positive. This moment is mz, and anti-clockwise it will be positive. If the moment is clockwise, it will be negative. That we may also consider, but now we are considering all for positive force and positive moment. Similarly, the displacement of node 2 will be denoted, the vertical displacement will be denoted by v. This is the displacement. And the rotation will be theta. Rotation will be theta z actually. The rotation will be theta. So if we want to determine the flexibility matrix, then we will apply force one by one. For stiffness matrix, we will apply displacement one by one. So first we will apply force one by one. So first we will apply the force. So let us say that is case 1. Case 1. So this is the cantilever beam. We are applying force here. Fy, we are saying that P. So if this is the force, then the displacement will look like this. And the displacement value will be PL cube by 3EI. And we are considering both the vertical force along y direction and vertical displacement along y direction. Along the upward direction, we are considering both as positive. So force P is positive. The displacement PL cube by 3I is also positive, as both are actually vertically upward direction. Now what will be the slope? This slope or rotation? This will be actually PL square by 2EI. From the basic concept of strength of material, we know that the slope will be PL square by 2EI. Slope will be PL square by 2EI. Now, this is case 1. So for case 2, this is our cantilever beam. We will apply some anti-clockwise moment M at node 2. We are applying anti-clockwise moment. Why? We are applying anti-clockwise moment because that is considered as positive based on our coordinate system. Now if we apply some anti-clockwise moment, again the cantilever beam will move like this, and this will be the displacement. We know the displacement value from basic concept of strength of material, and this will be ml square by 2EI. And the slope will be, this will be ml by EI. This slope or rotation, this is actually anti-clockwise in direction. And we are considering, for our particular problem, we are considering anti-clockwise movement and anti-clockwise rotation both as positive. So this will be the force and this will be the displacement. Now what will be the total displacement? Now total displacement, V will be equals to PL cube by 3I plus ml square by 2EI. This is from case 1 and this is from case 2. What will be the total rotation or slope? It will be PL square by 2EI for first case, and it will be ml by EI for the second case. Now if you want to form the flexibility matrix, then along the at the left side there will be V and theta, and at the right side there will be P and M. Now what will be this term? This term will be P into L cube by 3I. This will be this. This will be L cube by 3I. What will be this term? This term will be M into L square by 2EI. So this will be L square by 2EI. So this will be L square by 2EI. So V will be P into L cube by 3I plus M into L square by 2EI. Similarly, for theta, it will be P into L square by 2EI. So here there will be L square by 2EI and M into L by EI. So here there will be L by EI. So, and this is our flexibility matrix. So this is our flexibility matrix. And here you can also see that this particular matrix is square matrix. Obviously it will be square matrix with 2 degrees of freedom. Here for node 2 there are 2 degrees of freedom. So this matrix will be actually 2 by 2 matrix. Because 2 degrees of freedom, so there will be 2 row and 2 column. Now the important thing is that interesting thing is that actually both this term is same. But this term L square by 2EI, this comes from this part. m into L square by 2ei, which is actually the deflection for second case. That means when you are applying moment m, at that time the deflection is ml square by 2ei. And this pl square by 2ei, this is actually the slope for first case. When you are applying force p, at that time the slope is pl square by 2ei. So one is slope for force, another is deflection for moment, but still the values are coming same. So this is also one very interesting part of Maxwell's reciprocal deflection. That means that if we apply unit force at one particular point, if we apply unit force 1, what will be the slope? That value will be equals to, when we are applying unit moment at this node, that will be the deflection. So both will be same. Sorry, this will be slope. So the value of this theta and this delta both will be same. So if we apply same value of force and moment, like suppose this is k, this is also k. So the slope generated due to force k will be equals to displacement generated due to moment k. So this is very interesting thing, that slope generated due to force k will be equals to displacement generated due to moment k. So this is also very interesting form of Maxwell's reciprocal deflection. So, and this is our flexibility matrix. So this is our flexibility matrix, which is symmetric matrix. So now we will go for the stiffness matrix. So again, same our cantilever beam problem. This is node 1 and this is node 2. For cantilever beam problem, we do not apply force or moment. We apply displacement. Now, how we apply displacement? Initially, we consider that both joint is fixed joint. Both joint is fixed joint. And suppose we are providing V at node 2. That means we both joint is fixed joint, but we are providing displacement V at node 2. So when we will provide displacement V at node 2 along the upward direction, the shape of the beam will look like this. And this is a very common case of structural analysis. The sway of a particular, the movement of a particular joint. And when there will be some movement of a particular joint, there will be some moment. And we know the value of the moment. The value of the moment for this case will be 6 ei v by L square. And here also it will be 6 ei v by L square. Now this moment will be clockwise or anti-clockwise. That concept is very simple. Like if both joint are hinge joint, at that time this will be the shape of the deflection, shape of the deflected beam. But as both the joint are fixed joint, so slope at both this joint will be 0. So the deflected shape will look like this. That means we can actually assume that we are actually giving some more moment to make the slope 0. So we are actually providing the restraining moment, and that this will be the direction of movement. Because if a beam is trying to move in this direction, and if we want to change the displacement direction, at that time we have to give some moment here, and that will be obviously it will be clockwise in nature here, and here also it will be clockwise, and that value will be 6 ei v by L square. So both are clockwise in nature, and total is 6 ei v by L square, total moment 6 ei v by L square plus 6 ei v by L square. So total is clockwise unbalanced moment of 12 ei v by L square. So some reaction force will generate, which will create some anti-clockwise moment, and that anti-clockwise moment will be also 12 ei v by L square. Now if the reaction force is 12 ei v by L cube, 12 ei v by L cube. Now if this is the direction of force, then this two force will also generate the moment 12 ei v by L cube into their lever arm, their distance. The distance of these two forces are also L. So the moment due to this force will be 12 ei into v by L cube into L. So it will be also 12 ei v by L square, and it will be anti-clockwise in nature. Here it is clockwise in nature. So these two will actually counter each other. So now the reaction force will be 12 ei v by L cube at node 1, and for node 2 it will be also 12 ei v by L cube along the upward direction. So upward direction, we know that this force is positive. This force will be obviously negative because this is the downward direction. Now for moment we know that for our particular coordinate system, the anti-clockwise moment is positive. So this moment will be negative. This will be also negative because both moments are actually clockwise in nature. So this moment will be negative. So these are the different forces that are generated at both the support when we are providing displacement V at node 2. When we are providing displacement V at node 2 along the positive y direction, then these are the different forces. Now case 2. This is node 1. Now we will provide theta at node 2. Initially it was fixed support, but now we will provide theta at node 2. Providing theta means we are making this support as hinge support, and we are providing theta here. This rotation is theta. If this is fixed support, then there will be no theta, because for fixed support there will be no slope. So we are changing the fixed support to hinge support, because now we are trying to add some particular amount of rotation which is theta. So now if we provide the value of rotation which is theta, then what will be the moment at this particular node? The moment will be 4 EI by L into theta. And if the rotation is anti-clockwise, the moment will be also anti-clockwise. So this will be the value. Now what will be the moment for node 1? That will be also anti-clockwise. And the value will be 2 EI by L into theta. I think you know about the concept of carryover moment, which is very much important for moment distribution method. From moment distribution method, we know that if we apply moment M at this particular joint, at the hinge joint, then the moment that will develop at the far end will be half of this particular moment. So this will be the half of 4 EI by L into theta. So this will be 2 EI by L into theta, and for both cases the direction will be same. Now both 4 EI by L into theta and 2 EI by L into theta, both are actually anti-clockwise in nature. So again, some force will develop at both this joint, which will create some clockwise movement. So if the reaction force, the direction of reaction force is like this, then these two reaction force will create some clockwise movement. Here actually the unbalanced anti-clockwise movement is 6 EI by L into theta. This is anti-clockwise. So there needs some 6 EI by L into theta clockwise movement. So if our force is 6 EI by L square into theta, 6 EI by L square into theta, then here the moment will develop is 6 EI by L square into theta into L, the distance between these 2 points. So at that time also the moment will be 6 EI by L into theta. So the force will be 6 EI by L square into theta, because if the force is 6 EI by L square into theta, then the moment will be 6 EI by L into theta. So now what will be the force developed at node 2? Force developed at node 2 will be how much? The force will be, here it is 12 EI V by L cube in the upward direction, so it will be positive from the first case. From the second case it will be minus 6 EI L square into theta, because this force is downward. This force is upward, so it is positive, and this force is downward, so it is negative. So this is the force developed at node 2. What will be the moment developed at node 2? From the first case it is minus 6 EI V by L square. Why minus? Because this moment is actually clockwise movement. We are considering, based on our coordinate system, that anti-clockwise movement is positive. Here the moment is clockwise, so it will be negative. So minus 6 EI by L square into V. And from the second case, the moment is anti-clockwise in nature, so it will be positive, and the value is 4 EI by L into theta. So it will be plus 4 EI by L into theta. So this is our force and moment. So now if you want to develop the matrix, the matrix will look like this. Again, this particular matrix is square matrix, because here our degree of freedom is 2. So this particular matrix is 2 by 2 matrix. This matrix is square matrix. This matrix is symmetric matrix. These two terms minus 6ci by L square, these two terms are actually same. But again, if you look at both this case, the thing are quite opposite. Because for the first case, this minus 6ei into v by L square, this is actually the moment developed due to the displacement v. And this is the force developed in second case due to the rotation theta. This is the force developed due to rotation theta. This is the force developed due to rotation theta. And this is the moment developed due to displacement v. So this is the force developed due to rotation theta. And this is the moment developed due to displacement v. So this is again some interesting result. But still, the matrix is symmetric matrix. So here, this is our stiffness matrix. So if we again write the stiffness matrix, then this is the form 12 ei by L cube minus 6 ei by L square minus 6 ei by L square and 4 ei by L. What is the flexibility matrix? So this is the stiffness matrix and this is the flexibility matrix. If we multiply these two matrices, the first term will be 12 ei by L cube, this term is same. If we multiply these two matrices, then first term will be 12 ei by L cube into L cube by 3ei. So it will be 4. Then minus 6 ei by L square into L square by 2ei. So it will be minus 3. Now the second term, this term will be 12 ei by L cube into L square by 2ei. So it will be 6 minus 6 ei by L square into L by ei. So it will be minus 6. This term, the third term, this will be minus 6 ei by L square into L cube by 3ei. So it will be minus 2. Then 4 ei by L into L square by 2ei. So this will be plus 2. This fourth term, this will be minus 6 ei by L square into L square by 2ei. So it will be minus 3. Plus 4 ei by L into L by ei. So plus 4. So this matrix will be 1, 0, 0, 1. So this is our identity matrix. So stiffness matrix into flexibility matrix will be equals to 1, identity matrix. So this is the basic property of stiffness and flexibility matrix, that the inverse of flexibility matrix is actually the stiffness matrix. So when we are doing the problem, one thing you have noticed that actually the formation of flexibility matrix is little bit simpler than actually the stiffness matrix. But when we will go for a real life problem, at that time we will see it again and again that stiffness matrix is more efficient. Because normally we know that for a large building, if we provide displacement at a particular node, then the effect of that displacement is actually localized. The effect of that displacement will be actually localized in the nearby region. But when we will apply some force, the reaction will actually generate a different node. So that is one important thing. So now if we go for a side-by-side comparison of stiffness and flexibility matrix, then actually for stiffness matrix, the displacements are unknown. For flexibility matrix, forces are unknown and we are applying the force. For stiffness matrix, we will apply the displacement. For flexibility matrix, we will apply the force. Stiffness method is also known as displacement method and flexibility method is known as force method. Now another thing is also very important for stiffness matrix is that normally stiffness matrix are sparse and banded. Banded means normally if we go for a large stiffness matrix, then we will see that actually most of the element will be concentrated along the principal diagonal and other term will be 0. This term will be 0. Most of the non-zero term will be actually concentrated along the principal diagonal. But for the flexibility matrix, most of the term will be non-zero. Most of the term will be non-zero for flexibility matrix. But for stiffness matrix, many term will be 0 and most of the term will be concentrated near the principal diagonal. So this matrix will be known as banded and sparse. This is one of the important concept of matrix method, that when the matrix is containing many zero term, at that time it will be sparse matrix and its calculation will be easier. So this is very important thing, and that's why also stiffness method is actually more common and more efficient than the flexibility method. Both matrices are actually symmetric matrix. And another thing is also very important, that for stiffness matrix, it is very simple to actually combining the data from different matrices. If there is a large element and if we can generate the stiffness matrix for different element, then very easily we can actually combine the data from this different element. From the different matrix, we can actually combine the data and we can form the combined matrix very easily. But for flexibility matrix, that type of thing is not that much simple. So if I say all that thing, then it will be not very clear to you. But you have to remember one thing, that actually stiffness matrix will be always much more efficient than the flexibility matrix method. So that is all. Hope you have been able to understand that how we can generate flexibility and stiffness matrix. Thank you for your attention. Thank you.